Hello and welcome to our Math to Market online seminar. Today's topic will be GeoDict Insights, determination of fiber length distributions with FiberFind-AI. My name is Oliver Rimmel and I will be your host today. Together with my colleagues, I will give you an introduction in working with fibrous materials in GeoDict. Let's start with the motivation for our work shown here. Fibrous materials are used in a variety of applications. Fiber length is a key parameter that significantly impacts the performance and properties of many materials and products. Whether in nonwoven materials or composite structures, the length of the fibers can influence their functionality and overall effectiveness in various applications. In the case of nonwovens, such as filter components, hygiene products, medical materials and construction items, fiber length determines crucial product properties like permeability, capillary pressure curves, and mechanical performance. For example, in filters, fiber length can affect how efficiently particles are trapped. In hygiene and medical products, it impacts softness and strength, while in construction, it contributes to insulation and durability. On the other hand, for composites like injection molded or SMC parts, fiber length and orientation plays a pivotal role in the manufacturing process and the design aim. Longer fibers often enhance the mechanical performance of composites, providing better strength and stiffness. Meanwhile, shorter fibers may be more suitable for intricate designs or faster production cycles. Ultimately, understanding and optimizing fiber length is essential to achieving the desired properties and performance of these products, ensuring they meet both functional requirements and design objectives. We will now start with a short introduction of Math to Market and GeoDict. After that, we proceed with how a microcity of a fibrous material is captured and analyzed. Subsequently, we will move on to analysis of fiber length and much more with FiberFind-AI. But first, let me introduce myself. My name is Oliver Rimmel. I studied mechanical engineering at the University of Kaiserslautern with a focus on material science and composite materials. After this, I joined the Leibniz Institute for Composite Materials in Kaiserslautern as a scientific assistant in the Department of Manufacturing Science of Composite Materials. I concluded this work with a PhD in the field of experimental and simulative analysis of composite impregnation processes. After this, I worked at PFW Aerospace in Speyer in the field of additive manufacturing for titanium materials. In 2022, I joined Math to Market as a business manager for digital materials R&D. This field includes, but is not limited to, composites, nonwovens, technical textiles, ceramics, metals, foams, and additive manufacturing. Later in the session, my colleague Lilli will give you detailed insights in using GeoDict. Lilli, please introduce yourself.
Thank you for the introduction, Oliver. My name is Lilli. I studied applied mathematics at the University of Paderborn, focusing on numerics and mechanical engineering. Afterward, I moved to Kaiserslautern to join the Fraunhofer Institute for Industrial Mathematics. There, I initially worked on my PhD in the field of simulating operational loads for maintenance purposes. Later, I concluded my work as a scientific employee in the areas of physics and data-driven modeling and simulation of dynamic systems. From 2023 to 2024, I worked as a data science engineer at KSB in Frankenthal, and since March this year, I have been working as an application engineer in the support team of Math to Market, focusing primarily but not exclusively on applications in digital material R&D.
After that, we continue with our company. Math to Market is a leading company specialized in the creation and marketing of the engineering software GeoDict. Established in 2011 as a spin-off from the Fraunhofer ITWM in Kaiserslautern, the company remains privately owned and headquartered in Kaiserslautern, Germany. GeoDict is widely recognized as a cutting-edge tool for analyzing and designing the microstructure of porous media and composite materials. Known as the Digital Material Laboratory, GeoDict enables engineers and researchers to compute material properties and simulate material properties with high precision. The software supports a variety of input methods, including 3D scans from microcity and FibSim devices, as well as its own generated geometric material models. It also accepts CAD input data, allowing users to work with complex designs such as filter casings and other components. By combining advanced simulation capabilities with flexible design options, Math2Market and GeoDict empower industries to optimize materials and innovate with confidence. At Math2Market, our team embodies innovation and excellence. We are a group of 65 talented individuals, of whom 42% are women. With 39% of our workforce holding PhDs, we are proud to say that we are not just a team, we are a powerhouse of expertise. Our specialists in the different fields bring deep knowledge and experience in software development, physics, and mathematics. This foundation is further strengthened by chemists, physicists, and engineers from different areas with their understanding of the specific application areas we serve, ensuring that our solutions are not only technically advanced, but also practical and impactful. From developing pioneering software tools to tackling complex challenges in material design and engineering, we are passionate about what we do, and it shows. This passion drives our mission to deliver world-class solutions while fostering a workplace culture that celebrates creativity, inclusivity, and technical excellence. At Math2Market, we don't just work hard, we love what we do, and that makes all the difference. GeoDict is a groundbreaking solution for data-driven digital material design, combining innovation with ease of use. As a comprehensive material simulator, GeoDict provides the most complete set of tools for multi-scale 3D image processing, material modeling, and property characterization. The software enables users to analyze, simulate, and optimize material and processes, all within a single integrated platform. GeoDict excels in processing 3D images from microCT or FibSim scans, allowing users to visualize and model the microstructure of materials in unprecedented detail. Additionally, it supports the creation of synthetic material models, reducing or even eliminating the need for physical samples when experimenting with new designs. When it comes to material characterization, GeoDict offers robust tools to calculate key properties such as permeability, thermal conductivity, and mechanical performance. These features enable precise evaluation and ensure materials meet the desired specifications. Beyond this, its simulation-based development tools allow for predicting material behavior under real-world conditions, helping optimize both designs and production processes. Despite its advanced capabilities, GeoDict remains user-friendly, designed for accessibility by both beginners and experts in material science and engineering. From research labs to industrial applications, GeoDict empowers users to accelerate innovation and make data-driven decisions efficiently and effectively. With GeoDict, material design is no longer limited by guesswork or time-intensive trials, it's a streamlined digital process built for the future. I bet you are wondering by now in which areas the software can be used. The great news is there's many of them. In filtration, GeoDict helps customers understand, optimize, and redesign filters. By modeling the complex interplay of filter media properties, fiber arrangements, and fluid characteristics, GeoDict enables manufacturers to improve existing materials and develop new filter media, pleats, and housings, reducing experimental costs and efforts. In electrochemistry, GeoDict drives innovation in batteries, fuel cells, and electrolyzers. For batteries, GeoDict enhances energy density, durability, and eco-friendliness, tackling challenges in energy storage. In fuel cells, it improves microstructures to boost efficiency and performance, and for electrolyzers, GeoDict optimizes porous tensor layers for better efficiency and longer lifespan, advancing green hydrogen technologies. GeoDict accelerates development, reduces costs, and drives sustainable innovation. GeoDict also revolutionizes digital material R&D for nonwovens, forms, and composites. For nonwovens, GeoDict analyzes microCT scan, uses AI to identify fibers, and creates 3D models to optimize permeability, strength, and thermal conductivity. For composites, GeoDict simulates permeability, fracture mechanics, and anisotropic stiffness, streamlining design for high-performance materials. In forms, GeoDict simulates microstructures to adjust parameters like cell size and distribution, predicting performance before prototyping, saving time and resources. In the energy sector, digital rock physics transforms core analysis for reservoir modeling. DRP supplements, digitalizes, and automates routine and special core analysis, and enables faster, cost-effective analysis, allowing multiple experiments on the same sample and simulating different production scenarios, ultimately informing field development decisions and reducing time to production. Finally, image processing and analysis through MicroCT and FibSem provide crucial 3D insights into material microstructures. GeoDict streamlines the process, converting raw data into precise digital twins. With advanced segmentation tools and AI, GeoDict accelerates material analysis, providing faster, more accurate insights to drive breakthroughs in material design. We are extremely proud to showcase some of our valued clients here, representing a range of industries and application areas where GeoDict is making a difference. These logos highlight the diversity and innovation we are part of, from filtration to electrochemistry, material R&D, DRP and beyond. In fact, while we are honored to display these names, we have around 450 clients that we are equally proud of their trust and collaboration. And of course, we'd be delighted to add anyone in the audience to this slide in the future. Thank you for being part of this journey with us. Now that you got a first impression of Math to Market and GeoDict, we'll dive deeper into how to set up a digital material development process. We get started with MicroCT analysis of fibrous materials. Here's an exemplary development process for a composite. What we mean with digital material analysis and design is shown in the workflow on this slide. It often starts with the import of a 3D image on a physical sample. Afterwards, the image is analyzed to understand the material and its properties. This step alone can already be very useful. At first, an understanding of the geometric properties of the material is needed. With this knowledge, you can then start to create your own statistical digital twin. Having this twin, one can start to design or engineer a next-generation material with improved properties. In this way, GeoDict can help to design improved materials faster and cheaper. In the following presentation, we will focus on identifying and analyzing single fibers in a CT scan to measure a fiber length distribution in a material such as a nonwoven or composite. But let's start with the reasons why we think that the experimental determination of fiber length might not be the best way to go. Measuring fiber length is a crucial step in characterizing nonwoven materials and composites. However, experimental measurement of fiber length is anything but straightforward due to several challenges. First, the random orientation of fibers in these materials makes tracing their path highly unpredictable. Additionally, fibers are often intertwined, further complicating the process of isolating and measuring individual fibers accurately. For composites, the problem is even more challenging because fibers are embedded in a matrix, which may require careful and often destructive removal to access the fibers for measurement. Another issue is length variability. Fibers in these materials can vary significantly in size, which means that extensive sampling is required to get representative measurements. Furthermore, fragility becomes a concern, especially with fine fibers, as they can easily break during handling or testing, introducing errors. Finally, traditional measurement methods are limited. They are often labor-intensive, time-consuming, and lack the precision needed to reliably measure fibers in complex materials like nonwovens or composites. This is why advanced automated tools and simulation-based methods, like those offered by GeoDict, can revolutionize fiber length measurement, overcoming these limitations while saving time and improving accuracy. Let's explore how these innovative solutions work. As mentioned before, we would like to start with a MicroCT scan. For the background of such a scan and how it works, we invited Mr. Markus Hennecker from RJL Micro and Analytic. MicroCT, or microcomputed tomography, is a non-destructive imaging technique used to capture the internal structure of a sample in high detail. Here's how it works. First, X-rays are generated and directed at the sample. As the sample rotates, X-rays pass through it at different angles. The varying densities within the sample cause different amounts of X-ray absorption, and this data is collected by a detector. The collected data is then used to reconstruct a detailed 3D image of the sample's internal structure. This process produces a volume image made up of gray values, where the intensity of the gray corresponds to the material density within the sample. This reconstructed volume image is the starting point for further analysis in GeoDict, enabling advanced simulations and material property evaluations. To give you a little bit more insight on what such a MicroCT device looks like and cost of this analysis method, I would like to hand over to Dr. Markus Hennecker from RJL Micro and Analytic, a partner we often work with on projects.
Welcome, dear participants. It is a pleasure to introduce our company. Analytical services and instrument sales from a single source. This is the motto of RTL Micro and Analytic. Our testing laboratory is located near Karlsruhe in Germany. Our services are accredited according to ISO 17025. We also sell scientific instruments and offer support and technical services to our customers. For further information, my colleagues and I are available by phone or email. I would like to give you an insight into our laboratory equipment and pricing. We operate microtomography scanners for almost any object size and image resolution. We offer scans on SkyScan tabletop scanners for high resolution or very large objects. We can also provide scans with true submicron resolution. Prices range from 380 to 1,075 euros, depending on the requested resolution. Please contact us and we will advise you on the best solutions.
In the following demo, my colleague Lilli Burger will show you how easy it is to work with 3D CT data in GeoDict. As mentioned before by Mr. Hennecker, the result of the micro-CT scan is a volume image with gray values. Depending on the hardware and processing, there's a wide range of gray values that can be distinguished by the user when looking at the scan, but is not yet useful for conducting analysis or doing property predictions. To get a segmented image that has an assigned material ID for each voxel, we first need to conduct some further steps. The first of this is image processing, like you know it from digital images of your camera. We can use image filters, crop and align the image, and much more. After this, we can use different methods to convert the gray values to distinct material classes, the so-called segmentation. During the demo by my colleague Lilli Burger, you will see all the needed steps from importing over image processing and segmentation of the different materials. The segmented structure is a representation of the material in which distinct materials are assigned to each voxel. Let's get started with the demo.
In the first part of the demo, I want to show you how to import, process and segment 3D CT data with GeoDict's Import GeoVol functionalities. Therefore, go to the Import option and select Import GeoVol. After selecting, you can see at the bottom left of GeoDict's main user interface that the module has been activated. By clicking on the Browse button, a file dialog opens and allows you to search for the dataset you want to import. For this demonstration, I choose a TIFF image stack stored in my input data folder. You can find this dataset named long fiber composite 4 micrometer as an example in the gray value datasets folder of your installation directory. We select one of these images and click on Open. Now the geometry import dialog opens. The dialog requires multiple parameters to be set, which I will not explain all in detail. Please refer to our online seminar Transforming 3D Scans into 3D Microstructure Models, which is available as a video tutorial. I will concentrate on the functionalities we need for the segmentation of our fiber composite example. We can leave all settings on default and click on Image Processing. Now the dataset is loaded into GeoDict, and we can have a first easy impression by visualizing the 3D option. Additionally, the 3D image processing dialog opens. It consists of multiple sections. The loaded fiber composite images are visualized in the 2D slice visualization area. You can see one slice for each of the 3 directions, and you can see each slice in the corresponding 2 other directions marked in the color of the boundary box of the slice. On the left side of the 3D image processing dialog, we have the image processing and the segmentation and labeling tab, which gives us access to all processing and segmentation functionalities. For processing the data, we have multiple functionalities available in GeoDict. For example, we can change the image size, the alignment of the images, or modify the gray values. We also have a large variety of filters available to improve the quality of your images for later segmentation. By filtering the data, artifacts from the measurements or noise can be eliminated. The filter we want to apply to our data is the non-local means filter, which can be accessed by going to Image Filters and choose the first option, the non-local means filter. This is a very powerful tool to reduce noise and is useful for many types of datasets. 3 parameters determine the behavior of this filter. For our dataset, a good parameter choice are a batch radius of 1 voxel, a search window of 3 voxel, and the filter strength of 0.15. Applying these parameters to our dataset results in a clearer image where noise is reduced in all slices. Now we want to segment our image dataset to get a digital material for further analysis and simulations. Therefore, we navigate to the Segmentation and Labeling tab. At this point, I want to mention that while it is indeed possible to handle pores in the matrix with GeoDict, I will not do this for this demonstration, as this has no influence on the fiber length distribution. One method I want to present today is the global thresholding method. If we expand the section, we see a variety of options to set up the segmentation. And if we click into this section, the segmentation overlay is activated. As you can see in the segmentation overlay view, the fibers are marked as red and the matrix is marked as white. Depending on the visibility slider position, we decrease or increase the transparency of the overlay. This allows us to compare and evaluate the segmentation result to our image dataset. After changing the name of the result, which is Segmentation Global for Global Threshold Seminar, we can start the segmentation process by going on Create Segmentation. As soon as the segmentation is finished, you can view the result in the main user interface. The global thresholding functionality is a very straightforward and easy method to segment an image dataset, but it might be not sufficient enough for all datasets. Therefore, we have a very powerful AI segmentation functionality. In GeoDict, there are 4 different AI methods. Boosted Tree and Random Forest are comparatively fast AI models that require little training data but may be limited in their learning capabilities and are therefore more useful for simple structures. The Unit 2D and 3D models are very computationally expensive and require a lot of training data, but are very powerful as they are able to learn very complex structures and segment them properly. Our dataset is quite simple, so we can use the Boosted Tree method for demonstration purpose. Our fiber composite structure consists of polypropylene as a matrix material. We can take this from our database, and our fibers consist of glass. All other parameters except of the name, once again, can be left on default. Before we can start to train our AI model, we need to provide some training data. Therefore, we need to label our dataset by painting the different materials in the corresponding colors directly in our dataset. We recommend to switch to the stacked view mode and label the Z slices. Therefore, we need to switch from the navigation mode to the painting mode. We will start with the matrix material in white. We will see the paintbrush if we move our mouse over the image. Then we can easily paint the matrix material in white and corresponding the fiber materials in red. Therefore, we might need to decrease the size of the brush. If you have painted enough matrix material and fiber material for your labeling, you can save these labels and load them afterwards. This is what I have done. I have prepared some labels which I want to load now. Now you can see the previously defined labels which we can now use as AI training data. You can start the training process by clicking on Train. After the model has been trained, you can check the quality of the trained model with a preview function, which calculates the label forecast for every direction. If your result is sufficient, you can use this AI model to generate a digital model of our fiber composite structure by clicking on Create Segmentation. Again, the created structure now is loaded into GeoDict's main user interface. After the structure has been approved by the user, it can be used for further analysis as the determination of the fiber length distribution with GeoDict FiberFind-AI, which I am going to discuss in the next part of the seminar.
Now that we have a segmentation of our query value image into different material classes, let's get started with analyzing the sample. To do so, we use our module FiberFind-AI. FiberFind-AI is a powerful module that leverages neural networks to analyze and label individual fibers in CT scan data. By using advanced machine learning algorithms, FiberFind-AI can automatically detect and identify each fiber within a 3D scan, providing detailed, accurate data about the geometry and characteristics of each fiber. Thanks to this technology, we gain valuable insights into key parameters such as fiber length, fiber diameter, fiber orientation, and fiber position. This allows us to build a comprehensive profile of the fiber network in the scanned material. One of the standout features of FiberFind-AI is its ability to calculate a range of statistical metrics for fiber properties. For example, we can easily generate a fiber diameter distribution, providing a clear picture of the variation in fiber sizes throughout the material. Similarly, we can analyze the fiber length distribution, helping us understand the range of fiber lengths present and how they might impact the material's performance. Moreover, FiberFind-AI can calculate fiber curvature distribution, offering insights into how the fibers bend and interact within the material. Additionally, the fiber orientation distribution shows us the alignment of fibers, which is crucial for understanding the mechanical behavior of materials like composites or nonwoven fabrics. These detailed metrics are invaluable for optimizing material properties and improving manufacturing processes. By having access to this level of detailed data, we can make more informed decisions, whether it's enhancing the strength of a composite, improving filtration efficiency in nonwovens, or customizing the structure of the fibers for specific applications. In summary, FiberFind-AI revolutionizes fiber analysis by providing granular, actionable data that enables deeper insights into fiber geometries, distributions, and orientations. With this data, we unlock new possibilities for optimizing and customizing materials to meet specific performance requirements. But now let's head back to the demo by my colleague Lilli Burger, who will show you how easy you can do this yourself in GeoDict.
In this part of our seminar, we want to discuss how to identify fibers from the created digital structure of our fiber composite sample and determine the fiber length distribution with GeoDict FiberFind-AI. As you can see here, the created structure from the segmentation step before is already loaded into GeoDict's main user interface. To activate the FiberFind module, you have to go to Analyze and choose FiberFind. In this drop-down menu, you can see the different functionalities of the FiberFind module. In general, FiberFind functionalities aim to understand 3D scans of fibrous materials like nonwovens or fiber-based composites, as it is the case for our example. Two distinct approaches are pursued in FiberFind. The first approach deals with the estimation of statistical properties of the fibers, which is the diameter distribution, the orientation distribution, as well as curvature and curliness, by using classical image processing methods. The second approach is to identify individual fibers and binder by AI functionalities and do the statistical property estimation on the basis of this identification. For the fiber length distribution, we use the Identify Fibers AI functionality. After clicking on Edit, the FiberFind Identify Fibers AI dialog opens. We can leave most of the parameters on default as this is the best choice for most applications. Only for our structure we need to change the material to analyze parameter. As our structure consists of two different solids, we need to select either chosen material to be glass for our fibers to identify, or chosen materials ID, which is 1 in our structure. Then you can close the dialog and start the identification process by clicking on Run. I have shortened the calculation step a bit for this presentation and will go directly to the result viewer. Once the identification process is complete, the result file opens automatically in the results viewer. In the first Results tab, the Report tab, an overview is given. So in our example structure, 7,711 individual fibers are identified. Additionally, some mean values describing the shape of the fibers and the structure are given in this table. All these identified information can be used to directly create a digital twin of the structure in FiberGeo. Switching to the Plots tab, we have a more detailed representation of the identification results. The first histogram illustrates the fiber length distribution, with the x-axis representing the fiber length in meter and the y-axis showing the relative count probability. The relative count probability indicates the proportion of observations that fall into each length category. If you want a more finer resolution of this histogram, you can go to the left side of the result viewer and change the number of bins. So for example to 40. Go to Apply and the histogram is calculated with a number of bins of 40. We also have the fiber diameter distribution plotted as a histogram with the relative count probability on the y-axis and the fiber diameters again in meter on the x-axis. On the next 3 tabs, the orientation histograms are shown. I will not explain the orientations histograms and the curvature and curl index histograms in detail and refer to the FiberFind-AI user guide. The next tab, Threshold by Scalar Value, is very powerful to run further post-processing analysis tabs. Here you can see the histogram for length once again, but this time calculated with 100 bins, and additionally the corresponding Gaussian fit. On the left side of the results viewer, you can see the parameters you can set for the tab Thresholds by Scalar Value. You can choose between 3 different thresholding methods. The k-means method and the Otsu method will calculate a threshold with the corresponding algorithm. Therefore, you have to define the number of different fiber types. So for example, if you want to distinguish the structure into 3 different fiber types, the thresholding method will calculate 2 different thresholds. The third opportunity, manual, allows you to set the threshold yourself. So for example, if you want to distinguish your structure into a set of fibers which are shorter than 1000 micrometer and a set of fibers which is longer than 1000 micrometer, you can set a threshold of 1 to the power of -3. We can go to Apply and update all results with respect to this threshold. All distributions will be updated, not only the one under Threshold by Scalar Value tab. But let's start with discussing the result here. So in green you can see now the threshold we have set manually and 2 different Gaussian fits, 1 for each class. If we go back to the fiber length distribution tab, we now see that both classes are marked in different colors. And as you can see in the Report tab, the results had been updated here too, and we now have the specification for 2 classes. Additionally, we have multiple result files which we can load into the GeoDict main user interface in order to analyze the identification result in more detail. So for example, let's load the G32 file into GeoDict's main window and now raise the main GeoDict user interface. So every fiber which was identified has another color, and you can have a check if the identification process worked well, if there are many splits between fibers, for example. Another very useful functionality is loading the curve fiber fit as GAD file into the main GUI. So here every single fiber in the structure is an individual object which you can select. Therefore go to the GAD object selection mode and choose a fiber you want to select. So for example, this one. And to have a closer look, you can change the material temporarily. So for example, to the material, the ID3. And then you can go to the color and visibility tab and uncheck the visibility for all glass fibers. And so you can have a closer look at only one fiber as an example. So we now reach the end of the second and final demonstration part. Of course, there are many other possibilities to analyze the Identify Fibers AI result, but I hope I could give you a good impression of what is possible and how the workflow looks like if starting with a TIFF image stack of a fiber composite sample and ending with a detailed analysis of the fiber length distribution and other fiber characteristics of all fibers in that sample. Thank you very much for your attention.
Let's come to a real example where digital fiber length measurement was employed. In the DigiLaugB project, we explored the comparison between experimental and digital methods for fiber length analysis for glass fiber reinforced polymer manufactured in injection molding. For the experimental approach, the FASEP method was used, which involves multiple steps. First, ashing was performed to remove the composite matrix and isolate the fibers. This was followed by a dilution process, ensuring that fibers could be individually analyzed under a microscope. Finally, microscopic analysis provided detailed insights into fiber length distribution. While effective, this process is labor-intensive and relies heavily on physical sample preparation. On the digital side, fiber length analysis was conducted using CT scan data and our FiberFind-AI. Remarkably, the simulations yielded results comparable to the experimental measurements as shown in the histogram. Both methods provided similar distributions, particularly for the weighted average fiber length. This comparison highlights the potential of digital techniques to replace or complement traditional experiments. With CT scans and simulation, we can achieve similar accuracy, but with the added benefits of reduced sample destruction, faster analysis, and repeatability. This is a significant step forwards in improving material characterization processes. Besides the detailed insights into fiber length, there's a lot of other interesting measurements that can be conducted after labeling the single fibers. For example, you can threshold the results in FiberFind-AI by the value of certain properties, namely fiber length, diameter, curliness, curvature, center of mass, angle to x, y, and z axis. In this case, the threshold was an angle to the x-axis of 25 degrees. Then the fibers are segmented into two different material IDs. That means that you will get every statistic for those material IDs separately. And you can load the structure in GeoDict in which the two different fiber types are distinguished. You can see that on the right, all red fibers have an angle to the x-axis larger than 25 degrees. It becomes quite obvious that there is a massive amount of them in the center. And they are not just misaligned, but form some kind of vortex. This can often be seen in parts manufactured in processes such as injection molding or compression molding, where flow velocities and the temperature of the melt show a gradient throughout the thickness. Imagine being able to predict how your product will behave under different conditions, without ever needing to build a prototype. That's the power of a digital twin. A digital twin is a virtual model of a real-world object used to optimize design, predict scenarios, and manage the product lifecycle. Whether you're working with car engines, turbines, water distribution systems, or traffic networks, a digital twin can help you identify potential issues early and improve overall performance. Now, let's focus on materials, where digital twins can be game-changing. Using GeoDict, you can create a statistical digital twin of a material, such as a non-woven structure. This starts with defining key properties like the fiber material, orientation, thickness distribution, and fiber length distribution. By replicating these parameters digitally, we can generate a nonwoven with the same physical and geometrical properties as the real material. Why is this so valuable? Because once the digital twin is built, you can experiment with changing geometrical parameters to optimize your material for specific applications, without expensive and time-consuming trial and error in the lab. By starting your development process with a digital twin, you'll accelerate innovation, reduce costs, and find the best solution faster. The future of material design starts here with a virtual model that makes optimization simple and effective. Something we would like to emphasize after this session: GeoDict is much more than just a tool for working with fibrous structures. It's a comprehensive platform for material modeling and property analysis. At the heart of GeoDict are its Geo and Dict modules. The Geo modules shown in the top rows specialize in importing and creating geometries. Whether you're working with fibers in FiberGeo, grains in GrainGeo, or even form structures in FormGeo, these modules provide powerful tools to design and visualize complex materials. Modules like WeaveGeo and BleedGeo extend this functionality to even more specialized structures. In contrast, the Dict modules, displayed in the lower rows, focus on predicting and analyzing material properties. These modules cover a wide range of capabilities, from studying porosity with PoroDict to evaluating conductivity with ConductorDict, and even analyzing fluid and mechanical behavior with FlowDict and ElastoDict. And that's not all. With FiberFind and GrainFind, you can identify and analyze specific features of your material, like the orientation of fibers or the distribution of grains, offering unparalleled insights for research and development. GeoDict bridges innovation and digitalization, making it your all-in-one solution for understanding and optimizing materials. If you want to know more about the possibilities of GeoDict, we have something for you. In 2025, our GeoDict Innovation Conference will once again bring together experts from science, research and industry for an event filled with engaging presentations, targeted breakout sessions and valuable networking opportunities. Of course, there's the possibility to either participate in person or online. Over 2 days, you'll have the chance to exchange knowledge on material research and development with leaders in the field. This is the premier event for professionals involved in simulation and material sciences. Remember, registration closes end of January. The event will take place at the Congress Center in Ramstein, Germany. Participation is free, but advanced registration is required. We look forward to welcoming you to the GeoDict Innovation Conference in February 2025. You will find further information and a registration form on our website. Before we wrap up, we'd love to stay connected and take the next step with you. You can simply scan the QR code on the screen to access our booking tool and schedule a meeting. Whether you're interested in trying out an evaluation license or starting a demo project, we're here to support you. We also invite you to follow us on YouTube and LinkedIn, where we regularly share updates, tutorials and success stories. It's a great way to stay informed and inspired. If you have any questions, feel free to ask them now, we're here to help. And if something comes to mind later, don't hesitate to reach out to us via email. Your feedback and curiosity mean a lot to us. Thank you for your time and interest. We look forward to connecting and exploring how we can help you achieve your goals.